Hi, my name is Jennifer Armbruster, and I will be discussing the Physics of the Piano lecture by Nick Giordano from Purdue University. I found this lecture extremely entertaining because I play both the flute, bassoon, and the piano, and I just never thought about the physics that go into the creation of those three instruments. To start, our modern piano has about 88 keys, but first, let's just take a trip down memory lane. The first piano, invented by Bartolomeo Cristofori in Florence, Italy, only had 49 keys. The piano included key parts that allowed the hammer to hit the spring while it was traveling freely. This piano was referred to as the pianoforte because an instrument was produced that could play both loud and soft. This was accomplished by using a hammer to strike the seams. This seems to only involve simple physics, that hit it hard, it's a loud noise, hit it soft, and it's quiet. However, that is so wrong. Before we get into the physics, though, let's just compare Cristofori's piano and the modern piano today. Back then, there were brass strings, and today we use steel strings. Back then, hammers were covered with parchment, and today the hammers are covered with felt. 49 notes versus 88 notes. One of the biggest differences is that the piano range evolved from 4 octaves to 7 1/3 octaves. The low end is set by the ability to perceive a tone, while the high end of the piano is set by the human ability to perceive tonal relationships, and those play into the importance of psychoacoustics. Now, why do we use wound strings in a piano? Why not just a thicker string? Wound strings are used to increase the mass per unit length, because if we didn't use wound strings, the piano today would be nearly 4 meters long. And the reason why is because we need to minimize string stiffness. For an ideal string that is perfectly flexible, standing wavelength frequencies are perfectly harmonic, which can be used by the equation frequency equals velocity divided by 2 times length. Winding adds very little stiffness to the string of the pianos. The effective stiffness is called inharmonicity, which deviations are not large, but they are definitely predictable, and it gives the piano tone a distinctive timbre. Octave stretching. Octave stretching can measure the inharmonicity in units called cents. 100 cents equals the spacing between notes. For notes spaced by an octave to sound good, note frequencies must be spaced by more than a factor of 2. Setting the string into motion. Hammers are attached to an escapement mechanism. The speed of the hammer depends on the key press. When a hammer is moving freely, it strikes the string. The hammer rebounds and wave pulses propagate away in both directions. Piano hammers are wooden and are covered with dense felt. The hammers in the largest are in the bass section, which is about a mass of 10 grams, and the smallest in the treble or the high notes weigh approximately 3 grams. Now, how should a string be modeled? First idea, model the hammer by Hooke's law, which would be the force equaling a negative constant called the weight of spring constant times the displacement of the string. However, that fails badly. So hammers are actually very nonlinear springs, which can be calculated by approximately multiplying the rate of the spring constant times the displacement of the spring cubed, and that's the difference. The effect of hammer nonlinearity is the hammer is effectively harder and harder for blows for the string. Harder hammer gives more strength at higher frequencies, and this means that the tone color can also change the volume. Hammer-string interactions are quite complex. Hammer stays in contact with spring during the return of initial pulses. The collision time also depends on the strength of the hammer blow. Now, let's look at the soundboard of soundboard physics. This thin piece of spruce, and the sound is generated by the motion of the soundboard. The soundboard motion is described by thin plate equation, familiar to the ones mechanical engineers use today. They have normal modes as found in any elastic system. They have breathing type modes with nodal lines, which has a fundamental frequency about 75 Hz. Bridges undergo a rocking motion, moving strings in directions perpendicular and parallel to the plane of the soundboard, and both polarizations are extremely important. The time delay for a single string, decay is not a single exponential formula. Having coupling between perpendicular and parallel motion of the springs gives a slow delay at longer times. Time decay. Some notes have 2 strings. Interactions cause the beating, and the physics is similar to the mixing of 2 degenerative modes. In conclusion, the piano tone is derived from simple vibrating springs, but the spring stiffness provides a unique tone color called inharmonicity. Overall, how hard you press the keys themselves will affect so many different aspects of the piano, and that is something I took away from this lecture. Overall, this lecture was really intriguing and extremely helpful to understanding basic physics principles and to an instrument that is used so openly today. Thank you.